All right, good afternoon, everyone. We're going to start today the third in our series of MRI lectures. We already went over the basics. Last week you saw how spatial localization is achieved in MRI, and today I want to talk a little bit about the signal that you're getting from the MRI and what that means for imaging quality, and also how you approach modifying or changing the signal. Of course, as always, if you have any questions, feel free to interrupt at any time and ask questions. MRI, like most things in imaging, is a great balancing act. You have this great technology at your fingertips, but everything is going to be a trade-off, and you have to weigh and counterbalance certain aspects and parameters of imaging against each other. The main things that we're going to be thinking about is you have the actual signal that you're getting out of the MRI machine from imaging the patient. You have background noise, which is going to work against you in terms of deteriorating your image. You have the acquisition time, which comes into play in clinical practice because you only have so much time for each slot to perform the exam. And also, if it's, say, a breath hold sequence or something like that, it may be important to control the exam time and make it shorter. Then finally, we'll talk about resolution, which is another parameter of quality of imaging. At the end of the day, basically the time you spend imaging and the number of protons you include in forming an image are going to equate to imaging signal, and the amount of imaging signal is going to determine basically the quality of your imaging parameters. So you can think of your signal as currency, and I like to think of it in terms of basically you either invest imaging time, which comes in many forms, TRT1, the number of experiments you're producing to get signal averages, whether or not you do a full case base versus partial Fourier acquisition, whether or not you're imaging your full echo or not, or you can invest in terms of the number of protons that you're imaging with each MR experiment. So that could be the strength of your magnetic field, the strength of your magnet, right? That's going to recruit more protons to be aligning with the magnetic field. TET2, that's timing in terms of how long you wait until you image. The field of view, you can include more protons at once, or flip angle, how much of each, say, slice you're going to be exciting before imaging. Anyway, you can invest these elements of imaging to get more signal, which I told you to think of as your currency, and then you're going to use that signal to purchase image quality, essentially. And then, imaging parameters are signal noise in the form of the signal to noise ratio, and also spatial resolution. Now, take note, you can run this in reverse, kind of like I was saying with imaging time. It may be that you have adequate image quality, but you're doing a breath hold sequence, so you want to gain back time. Or you can decide, you can make the conscious effort to say, I'm just trying to image lymph nodes or something, looking for metastatic disease, which are relatively large in comparison, so we're going to sacrifice some spatial resolution so that it's faster, so that the patient can hold their breath and you get a clear image. Whereas if you're, it's a 36-year-old with biliary colic or something, you're going to want to maximize your spatial resolution in an MRCP so that you can, really get down there and see small stones within the duct, which is also small. Okay, so this is how I want you to be thinking about things. These four central concepts, we'll call them signal and imaging quality. This is the end result, or what you're going to get out of the exam, what you're going to get out of the magnet, and then the effective proton number and imaging time. These are the things that are within your control that you're using to purchase these outcomes. Okay, so let's start by taking a look at just signal. People say signal all the time, so let's talk about signal in general. Well, I think it merits a 30-second introduction to signal detection theory, right? Well, what is signal detection theory? That applies in literally the detection of anything, because in the detection of anything, there's always noise, and signal detection theory is just the application of math and science to this central principle, and how to separate that thing, that anything that you're trying to perceive from the noise that necessarily surrounds it. Keep in mind, this is a pervasive concept. It's found everywhere. in your own vision, in your own hearing. Basically, the whole of statistics is devoted to signal detection, looking in sets of numbers for coherent signals in otherwise what it would be noisy data. Of course, measuring an MRI signal is no exception, and so this is a central concept in MRI. There's actually some really nice images that I pulled off the internet. I can't take credit for them, but this is an example of a low SNR image. There's always background noise in anything that we would otherwise image. It's just a matter of how much there is relative to the signal. Absolute noise doesn't even necessarily matter as much as it is a logarithmic ratio. Now, what does that mean? Well, the fact that signal to noise is measured in a logarithmic ratio means that by definition, it will be measured in decibels. That might sound confusing because you're used to hearing decibels as an audio thing. All right, well, decibels is not a dedicated unit for audio sound levels. Actually, the point of that is, the point to be taken away here is people describe human perception of auditory stimuli in terms of that signal and how it's presented relative to background noise, as in literal phonic noise in the atmosphere, and that's why it's measured in decibels. So this will be no exception. Hearing or seeing, in this case seeing the MR signal, is a result of that ratio. And you can see that in this simulation that somebody did, the signal is much higher than the background noise, and it's just much clearer to see. So this is basically what we're going for in terms of trying to image what we're trying to image when we're getting an MRI. So here's another look. If we think of when we're getting an MRI at its most basic step in the MR experiment, we're recording a waveform from within the bore of the magnet. So there's this signal, which we'll call this bump, as a current induced in our coil because of the oscillating magnetic fields from the protons within the bore, right? Now, there's also going to be noise. Now, the noise is going to come from literally 100 different sources. There's tons of noise because anytime you have an electronic component, anytime you switch the signal from one place to another, it goes across like a plug into a socket. Any of those things is going to introduce noise superimposed on that signal. So here you can see noise is just a random fluctuation. And basically the sum of the two is what you get in real life. So note that a receiver, so a receiving coil in an MRI machine, is going to simultaneously pick up both signal and noise. There is no way to actually separate these two, because if you could, then this talk would be pointless, because you just separate out the noise and that would be it. You'd have perfect signal and all the images would look beautiful, which we know is not the case. So, okay, that's what we're going to be focusing on. Just a quick, so get out your phones and go to www.polev.com/Walled, W-A-L-L-E-D. Then we're going to check for understanding. There's going to be a few different questions in this lecture. So the first question is, noise can be eliminated from an image by which of the following strategies? Is it multi-point RF transmission, analog to digital conversion at the coil instead of at the MR console in the tech control area, proper room shielding and completely closed door, or it is impossible to eliminate noise? Okay, good. So 100% of you correctly said that it is impossible to eliminate noise. So actually the first three choices all actually do reduce noise, or at least imaging artifacts. The first one reduces imaging artifacts. But the point is just so that you know there is no way to completely get rid of noise. All right, let's take a look at these two images. Let's say you're testing out some night vision goggles. If you look at goggles A and goggles B, which imaging parameter is clearly much higher in goggles B? Is it the spatial resolution, the intrinsic gamma, the signal-to-noise ratio, or the refresh rate? Okay, so 100% of people said signal-to-noise ratio. That's very good. I'm actually really impressed. People are often tempted to say, well, goggles B looks better. And so they are tempted to say the spatial resolution's higher, but I see that I've taught you guys well, so very good. It is the signal-to-noise ratio. And we're going to talk about that difference here right now. That's just your basic introduction to signal. Let's talk about what quote-unquote imaging quality means. All right. So perceived imaging quality, when you look at a picture that you get from an MRI exam and you say, wow, this looks really nice, you might be tempted to think that means that it's high spatial resolution. That's usually the default thought. But actually, imaging quality is a combination of both spatial resolution and the signal-to-noise ratio. So let's look at these things one at a time, and we'll start with defining spatial resolution and looking at how we end up getting higher or lower spatial resolution. So spatial resolution is directional, so we can think about it two ways when we get our MRI images. First of all, there's the in-plane resolution. That's basically when you're looking at the pixel array in the image in front of you, how close together are they? What are the pixel widths? And that can actually be calculated by field of view over matrix size, right? So if you have a 40 centimeter field of view and 400 pixels, then 40 divided by 400 is a tenth of a millimeter for the pixel size. Okay, or a millimeter for the pixel size. Slice thickness sometimes is conceptually a little harder to think, but that's basically going to be your spatial resolution in the z direction. So remember, when we do that slice selective pulse, and we're only putting magnetization into the xy plane for a certain thickness of protons, we're basically saying that we're treating them all the same along the z direction. So if you have a change in anatomy from the front of your imaging slice to the back of your imaging slice, that won't be accurately represented. It's going to be treated all as one pixel dimension. So let's talk about what spatial resolution means exactly. Not very profound, but basically it's your ability to resolve two things in real space. And remember, MRI is a representation of real space. So let's just take a real space, and let's say we have two distinct real objects here. The yellow looks kind of like a Werther's original, and the blue Werther's original. And we're going to ask if we're able to separate these two in our imaging representation. So what do? Well, let's take an image. Right? Let's start with a low resolution image. So we make a pixel grid that's a 3x3 or a 3x3 matrix. And we look at the imaging representation at real space. Well, we got a green square. Obviously, we've kind of failed here, and we've really misrepresented what we're doing in real space. So let's increase the resolution a little bit, make a 6x6 matrix, separate it up. And well, now we got two rectangles. We see there's a yellow element and a blue element, but we got the shapes wrong. Right. So if we then continue to increase over many steps, and we say make a 256 by 256 matrix, we get this imaging representation, which now is maybe flattened, and we don't expect to have perfect exact replication of real space, but we're seeing there's a yellow oval and a blue oval, certainly much closer than we were doing before, looking at our pixels here. So the important thing to note from this example is that anytime you're imaging, whatever you set your pixels up to be your pixel sizes, know that whatever happens inside the volume of that pixel or voxel is going to be averaged when it's presented in the imaging space. That's why you're seeing, instead of a yellow oval and a blue oval, they get averaged over the entire pixel that you've designated, which is why you get a green square. Okay. Now this is a very important artifact that certainly could very well be on your test, the partial volume averaging, or partial volume artifact. And this is basically means misrepresentation of reality based on the coarseness of your pixel dimension selection. Okay. And so what's the fix to that? Well, the fix to partial volume averaging is always to increase your matrix size. Right, when we have the 256 matrix, we're at least getting a better representation of real space. Now, also, notice this happens in the slice direction, which is what I was alluding to before. If you had, let me kind of jump out of the focus of MR here just for the sake of example. If you're looking at a chest CT and you're looking at 5 millimeter thick slice sections, and there's a 2 millimeter granuloma or 1 millimeter granuloma. So you have a 1 by 1 pixel that's 5 millimeters deep, right? When you see that 1 millimeter granuloma, it may contain the entire cross-sectional area of your 1 by 1 pixel, but there's going to be 4 millimeters of air-filled lung parenchyma behind it, or behind and in front of it, in the Z direction, which is going to average with the volume of that calcium. So you're probably only going to get about a quarter of the volume of calcium. Probably when you look at that image, it's going to look like a 1 millimeter soft tissue nodule, right? That's partial volume averaging, and it's incorrect. If you were to switch over to a more isometric acquisition, where the pixels are 1 by 1 and 1 deep, then you would see 4 1 by 1 normal air parenchymas and a calcified nodule, because you would retain all of the density information, because it wouldn't be averaging. Does that make sense? Okay, good. Partial volume averaging, very commonly talked about, very commonly asked about on the test. That's why I kind of belabored the point there. All right, let's look at resolution and actually defining a resolution. Don Knotts has returned, and that's because there's a kind of a complicated issue here with resolution. I'm going to say, and for the purposes of our discussion and for your tests, you should treat it as if spatial resolution can be separated. So you can have different in-plane spatial resolutions in the X direction and Y direction. Okay, and that resolution is going to be the field of view divided by the matrix size. So here we have an RVOT image. The field of view is 39 centimeters, and the matrix is a square matrix of 384 by 384. So you divide the field of view by the number of pixels, which is the same as your matrix size, and you end up getting this 1 millimeter in both the X and Y dimensions. So that's the pixel width and can serve as a measure of your spatial resolution. Basically, it's saying something that's 1 millimeter is about the size limitation of what you can see in that image. Here's an LVOT image. Now this is done with a similar field of view, but the matrix is much smaller, only 224 by 192. So now notice, and I've separated out the equation, so you can actually calculate the spatial resolution in the X direction and in the Y direction, which are different for our purposes and for the purposes of your test. Either way, they're about 2 millimeters in this image. So here's a real example where spatial resolution is double in this image what it is in this image. And I want you to just kind of look at these two pictures and kind of internalize. This is almost like when we were looking at the night vision goggles, this is the opposite, where this is a difference in spatial resolution, not really signal to noise. And you can just tell that the edges are a lot sharper here than they are here. You just feel like if there was some tiny element you were looking for, you'd be better off finding it in the RVOT on the left. Okay? Questions? Okay. All right. So if the two images, which we're not seeing, there we go. If these two images were just, say, brain MRIs, even though they are not, they're pictures of a tiger's eye, which of the following matrix pairs of matrix sizes were likely set at the MR console? So I give pairs of imaging parameters for A and B. Which do you think would be the matrix sizes for A and B? All right, man, you guys are cruising. So yes, that is exactly correct. It is this one. You can tell you can see the pixelation in image B that what we're seeing here is partial volume averaging around the tiger's eye, right? That's why there's a less sharp border there, because parts of the white sclera and the black outer part of his iris are being averaged together, and it's so coarse that you can actually see the stepwise approach of this. So image A has to have been made with a much higher resolution, so a higher matrix size, say this one relative to this one, which is why C is wrong. In choice A, it is true that the matrix size for image A is double the matrix size for image B, but the matrices are so small here, you would literally see and be able to count 8 by 10 pixels, and there's clearly more than that here. So that's why that's the incorrect answer. And then 720p and 1080i are display resolutions beyond the scope of this discussion, but Anyway, they're in the reverse order. So, okay. Now, remembering that perceived image quality is a combination of both spatial resolution and signal-to-noise ratio, let's talk about what the signal-to-noise ratio is. Well, the signal-to-noise ratio is another determination of how good your image looks. It's a little bit more intuitively difficult, but basically you're looking at the average signal intensity of whatever the thing is that you're trying to detect, so the body that you're imaging or whatever. And the noise we can operationally define. Now this is turns out a pretty poor designation, but it's all we got for a quick and dirty look at the SNR, as the standard deviation of the signal in the background, because the background should be 0. So any standard deviation within that should be uniform. Any standard deviation within that should reflect how much baseline noise there is. So what you do is you draw ROIs for the thing that you're looking at, and an ROI in air. You look at the average signal intensity and you look at the standard deviation of the signal intensity. Then you divide the standard deviation for air, you divide the signal intensity, average signal intensity, by the standard deviation in air. So in this case, the SNR, signal-to-noise ratio, in the liver is about 100, right? Which means that it's very visible, which makes sense because you can clearly see the liver. Now let's look at the aorta. Draw an ROI there. We see that the aorta, because this is it's much brighter, we actually have a lot more signal there, and so the SNR in the aorta is about 200. So the SNR, the signal-to-noise ratio of the aorta in this image, is about double that of the liver parenchyma. Now there's a couple important things to note here. All SNRs in any image will always correct to the same background value. And any anatomy that has higher intrinsic signal for whatever that sequence is that you're doing will have a higher SNR. So that is fact and truth. Okay, but let's talk about something that's a little more important to our actual practice, which is the contrast to noise ratio. Because whether or not you can see a lesion when you're reading a CAT scan or reading an MRI depends on the contrast to noise ratio. Now the contrast is just basically the signal difference in two things divided by the noise, which again we're going to pretend is the standard deviation of a uniform background. So here, draw an ROI in the aorta and in the liver and in the air. And then you would calculate, so a calculated contrast to noise ratio would be signal in the aorta minus the liver, all of that divided by the standard deviation in air. So here, a contrast to noise ratio of 100, which means it would be very visible. And whenever you have a high contrast to noise ratio, you have good lesion detection. So, for example, that's why people do things like fat saturation and stuff. Now, big warning, the example I just gave, the example calculation is really, it's very artificial. It's not even correct. So contrast resolution is really only relevant when two things are located in physical proximity. So if the aorta ran right through the liver parenchyma, then that would make sense to call it a contrast to noise ratio. Here, like we could do that with a portal vein, or if there was a liver lesion. So let's do something a little bit more relevant. Let's actually look at a liver lesion in multiple different imaging sequences, including CT. Right, so basically we're not seeing anything there in the post-contrast CT. In the T2 with no fat sat, there's something there. With fat sat, it pops out, and then with contrast, you really see it. Now, in retrospect, we can say, okay, it's probably there on the CT. But certainly what we're seeing here is what I'm trying to tell you is the reason that we see these better is because there's a higher contrast to noise ratio. All that matters in terms of your signal detection, your seeing a lesion on an exam, is the contrast to noise ratio. So if we drew a bunch of ROIs on a PAC station, we could do these calculations of signal intensity of lesion minus adjacent background, all divided by the standard deviation of air. And we see that the CNR here is 1, which means basically not visible. 0 is completely invisible, and 1 is within the range of noise, so basically invisible. And then with T2, it goes up, With T2 with fat stat, it goes up even higher because we're taking the fat out of the equation. So we're resetting all of the grayscale dynamic displays of all the pixels here. And then T1 post contrast, because of the way that contrast is, in different tissues and the way the imaging parameters have been manipulated so that the images are T1 weighted, we now have a much higher contrast to noise ratio. And this really is at the heart, this is the crux of why we do different sequences in MRI and why we use different TEs and different TRs, and we give contrast, we don't give contrast. It all seems very confusing and arbitrary at times, but I just kind of want a little touch to reality here in that we do this for a reason, a very good one, and that's so that we can find cancer, for example. Okay, so just to practice looking at these numbers, in the case if you ever see a question like this, given the ROIs that I've drawn and provided you the numbers for what is the approximate overall signal-to-noise ratio in the image of the body? 100. 100% is at 100. Very good. That is exactly right. So it's, 900 divided by 9 is 100. Pretty easy. You guys are doing well here. All right. So approximately what is the contrast to noise ratio of this liver lesion, provided the ROIs that I've drawn for you? Okay. Almost everyone said 30. 30 is the correct answer, not 66. So let's take a look. All right, so the contrast to noise ratio is the difference in mean signal intensity between a lesion, that's 300, and its background parenchyma, so 180. 300 minus 180 is 120. So your intensity difference is 120 divided by the standard deviation of air, which is your noise background. 120 divided by 4 is 30. 0.4 would be basically not visible because that's close to 0. 3.5 also. And 5.7 would be pretty hard to see too. I mean, it's also a nice, you can see it reasonably well. It's not crazy bright, but 30 is a good estimate for what that would have been anyway. Okay, so we've talked a little bit about signal and what imaging quality means. Now it's time to talk about actual effective proton number and imaging time, and how that relates to the parameters that are with your control. I know you guys just ate. We went through that a little fast, but let's take a 5-minute break now, because the next part's a little math heavy, and I don't want your eyelids to get heavy. All right, welcome back. We are going to start the second part of the talk, where we were talking about the signal-to-noise ratio and different contributions from different parameters, especially those which you can adjust. There's a couple equations here, which can be rearranged in various ways. It's a little different for 2D versus 3D, and if you're looking at these things as you're studying for the exam, you're probably thinking, why do I have to know all this, and what the hell is going on? So what I've done is, I know it looks complicated, but I've selected one expression. It is an equation, but it's everything that you need to know regarding what they would ask you on the test about how does doing this affect the signal for that. And this is it. So it's one equation. It still looks complicated, but basically I'm going to spend the next 45 minutes or an hour going through every single term in this equation so that you can understand at least once why it is in the place where it is. So just to talk about the very basic mathematical principle of what this equation means, this is describing what happens to signal-to-noise ratio when you change one of these things. Either the relationship is going to be direct, which means in the numerator, or indirect, which means in the denominator. Direct just means it goes in the same direction. So increased field of view, increased signal. Increased slice thickness, increased signal. Decreased matrix size in the frequency direction, decreased signal. So top or bottom, whether it increases or decreases when you increase that parameter, or linear or nonlinear. Luckily for us, in terms of the things that alter signal non-linearly, they only do so as the square root. So you only have to worry if it's linear or as the square root of. And that just means basically, if it's linear, then when you double the field of view, you double the SNR. When you double the slice thickness, you double the SNR, right? If you double the MSF, you have the SNR, right? Because it's indirect relationship. When it's under a square root sign, then if you say quadruple the next, it gets bigger, but as the square root of 4, so your SNR would double when you quadruple the next. Great. Now, in addition to just having this, I want to, like I said, slowly go through everyone and see why they are. So I have some general guidelines. First of all, for pretty much the rest of the slides, I'm going to leave that equation in the upper right-hand corner so you can glance at it, refer to it whenever you want. Now, more measurements are going to equal more signal, right? So anytime in life, in general, in statistics, if you're doing surveys, the more measurements you have, the better your signal to noise is going to be. Remember that. The more protons you have, so the more protons you include when you're imaging, is going to give you more signal to be measured. The more time kind of equals more signal. Now, you got to be careful when you think about this because it can work against you too. A longer sequence is not always better. In general, say like a spin echo gives you a lot more signal than a fast gradient will. But that's a very complex statement, and there's a million and one reasons for that. Time can also refer to both the overall length of scanning time or the length of time that you're listening to each individual echo. Now, remember that more time can also mean that you're collecting more noise. So it's a pretty complicated issue. In general, a longer sequence is going to have more signal, but you just be wary of that one. If you have more resolution, you're going to have less signal, right? You can never get a free lunch. It's like you have more. If you have better spatial resolution, then you're going to have to be, by definition, dealing with less signal. Otherwise, we would just crank up the spatial resolution on every study we did and make it infinite, right? Okay, remember that noise is always random, and SNR is the central concept that we're discussing here. Technically, signal just means absolute signal, right? But really all that clinically matters is the signal-to-noise ratio, or the contrast-to-noise ratio, which is a derivative of two signal-to-noise ratios. When I say signal for the rest of the talk, basically I mean SNR. I'm not talking about absolute signal. So when I say, field of view increases signal, I'm going to mean field of view increases SNR ratio. Okay. So first thing is K. The base signal from a sequence depends on a bunch of things, okay? So what sequence it is it a spin echo or is it a fast technique? What's the field strength, 1.5 Tesla? What's the proton density? Is it a T1 or T2 weighted? What's the flip angle? What kind of electronics are you using? How strong is your gradient? All of these things come into play to alter the amount of signal that you're going to be getting out of the inside of that board. Now, I'm lumping all of these together as this capital K. This is the easiest one because you just ignore it, forget about it. And I'm being serious. Sounds kind of weird, but you should ignore it because when we talk about SNR, again, I want you to think about real life, looking at real images. What are we talking about? We're talking about the difference in signal-to-noise ratio between two different sequences. Or you did this, axial slices through the knee, and it looks like crap. What do I do now? Well, all the base stuff is going to be the same. You still want a T2 axial fast spin echo, right? So none of that's going to change. You just want to know, well, can I change my matrix size, or can I do more next, or how can I improve the image, right? And so these are the things we're going to consider. Also note that specifically the TE, the TR, and the flip angle, those are going to drastically alter the actual imaging contrast. What I mean by imaging contrast is it a T1 image, a T2 image, is it a gradient, T2 star image? And that's next topic. So again, ignore that stuff for now and just focus on the things that are in this equation besides K. All right. the field of views, and yes, slice thickness is actually kind of a field of view. These things are easily changed when you're doing an MRI. And here I've depicted basically your field of view in the frequency direction and in the phase direction. Now, the slice thickness is basically your field of view in the z direction, as we talked about earlier in the lecture today. If you increase your field of view in any or all dimensions, you're going to necessarily include more protons. You see the square has doubled, so the area is doubled. That means in the real space, you're including twice as many protons along this direction, along that direction, and possibly along the thickness direction, right? And as we said before, more protons equals more signal. Okay, so let's look. The next 10 questions are going to be all in the same format, which is I'm going to give you at the top of the screen, you just got an image from, doesn't matter what, I'm saying it's a cardiac MR image, and you don't like the way it looks, so you want to double the SNR. So if you go from the parameters at the top to one of the parameter sets at the bottom, which one is going to double your SNR? All right, man, you guys are dead on today. So yes, so field of view, see, now some of you may have thought that was actually, that the correct answer was not showing, or that it was kind of a bad question, and you're right. I have intentionally made some of these questions so that they're more like test questions and that they can be bad or misleading. So really, if you double the field of view, if I don't specify that that's the phase field of view or the frequency field of view, you kind of assume that it's square. And if I had doubled the field of view in 2 dimensions, then I would have doubled the field of view here and doubled the field of view there. So the SNR should be times 4. But there's no option saying that, so this is the only one that's correct. Technically, if I doubled both field of views, then it should be quadruple SNR. Does that make sense to everyone? It's still the best answer available, though it's a misleading, crappy question. Okay, now let's talk about the next. This one's a little less obvious. And there's some different terms. You know, I like to try and bring you up to speed on what the different terms are that are interchangeable. Here, NEX stands for number of experiments, and is the same thing as NSA, which is the number of signal averages. So you could see any of those 4 terms in any textbook, and they all mean the same thing. And that's how many times you're going to record an echo at a given, if we're talking about a spin echo sequence, at a certain phase encoding step, how many times you record it and then average it together before putting it into K-space as a line in K-space. Okay? Now, why does this work? Well, the real signal, when you measure the echo multiple times, the real signal adds linearly, and the noise adds to itself as the square root. Well, why does the noise add as the square root? It has to do with the sampling variance, because sometimes it's positive and negative, and it can cancel itself out, and it's the square root. So that's basically the hand-waving way of saying, I don't feel like showing you the mathematical proof of this, because you would definitely fall asleep. I'm already seeing yawns out there. So instead, let's do something a little more fun, or I think is fun. And we're going to look at this empirically. Basically, in Excel, we can generate data sets. Let's say we're just trying to image something where the signal intensity should come out as 50, right? But then we add a noise function to superimpose upon it. We can constrain that so that it doesn't go beyond a certain point. So now I've generated a data set of measurements that are supposed to be 50 but have a random noise fluctuation around them. Okay. Now, you can repeat this and generate multiple sets of data, and since the random fluctuations are independent, it just relies on a random number generator, you're going to see it's going to be like real data. Now notice that sometimes in these 2 measurements, 50 is where we're supposed to be. At this point, both our first and our second have added positive noise. So in the resultant additive overall signal, at this point, the noise is going to be much higher. In fact, even higher than we've constrained the noise to be allowed to get to. But in a case like this, the noise in one measurement is below 50 and the noise in another is above 50. So in cases like this, the noise is going to tend to cancel itself. And especially when you do this over multiple iterations, it all evens out in a very nice statistical manner, and it ends up averaging to the square root as you add it. Well, I know it's not good enough to just say, so let's look at the summed signals from a couple different experiments. Basically, I repeated this experiment 5 times and then added them together. Here's the first one, here's the first plus second, first 2 plus the third, so on and so on. Until this top row, you have 5 randomly generated noisy measurements, okay? And you notice that every time the signal is adding linearly, right? It should be 50. When you add 2 of them together, it should be around 100, it should be around 150, etc. But the noise is getting bigger. The noise fluctuations here are like this, and then they get bigger as you go up. So there is addition of noise, it's just not linear. Otherwise, they'd be all over the place. So the point is that the ratio of signal to noise is going to be increasing because the ratio that signal is increasing way outstrips the way that noise is increasing. So let's look at that. Here's some final data. I repeated the 5 experiments 3 different times, tabulated the results, and there's some things that we should look at here. Basically, our mean signal always follows this linear addition where it's about 50, 100, etc., up to 250. And our noise is certainly not adding linearly, right? Because if you look at 2 next, that's not double there. If you look at the signal-to-noise ratio, the average signal-to-noise ratio, you can see that from 1 next to 4 next, it does double, right? So that means that's proving our point up there, that the signal-to-noise ratio increases as the square root of the factor of next, right? So you quadruple next, your signal doubles. If you do quarter next, forget what that means theoretically, then your SNR will be dropped in half. Okay? Any questions? That's a little tough. Okay. So, stated alternatively, this is the actual, like if you want to kind of look at the math based on our observations, right? SNR for 1 next is just the signal divided by the noise for that experiment. And if we quadruple it, we've shown that the signal, when you quadruple it, is 4 times the signal of 1 next. And the noise is the square root of 4 of the noise of 1 next. So signal is quadrupled, noise is doubled. If you replace right there, that means the signal to noise at 4 next is 4 times over 2 times the signal to noise ratio of 1, right? So it's going to be a factor of 2. Notes for the more mathematically inclined to prove that this does work. Cool? Good. All right. So here's another set of parameters. Starting at the top, the image was of unacceptable quality. I want to double the SNR. Which of these 4 parameter sets will double the SNR relative to the top one? B, yes. Very good. Everybody got it right. So we just got done talking about next. No surprise. That was my target for the question. If you increase the next by 4 times, you're doubling your signal-to-noise ratio. Good. Okay. Now, let's move on to another one that's kind of a little hard to understand. MSP in this equation is meant to represent the matrix size in the phase direction, which is equal to the number of phase encoding steps. Okay, so just remember that. Basically, an increase in the matrix size in the phase direction is going to result in a decrease in SNR, right? Because it's an indirect relationship as the square root, because it's non-linear. So why is it decreased and why is it as a square root? Well, let's take a look. So the easier part is to explain why there's a decrease at all, and that's when you increase the number of phase encode steps or you increase the matrix size in your phase direction, you're increasing the number of pixels that are there, right? So we've in phase direction is up and down in the y dimension. We've doubled the number of pixels in the y direction, which causes an increase in spatial resolution. An increase in spatial resolution is necessarily going to cause a decrease in the number of protons per voxel, right? You know, when we had this pixel, there's all these nice protons in here, and we just cut that volume in half. So a decrease in the number of protons per voxel is going to cause a consequent linear decrease in SNR. Okay, so why is it not then linear? Why is it under the square root? It's because there's two competing processes here. And it's similar to the reason why you get a square root change with increasing nex. So you doubling the matrix size cuts the signal in half for the volumetric reasons and the number of protons reasons. However, also increasing the matrix size and the phase direction is going to increase the number of phase encoding steps you do. Remember, at least for the basic spin echo MR, the number of phase encoding steps is going to be the number of experiments you do. And remember that the number of experiments, increasing number of experiments, will increase the signal to noise ratio. So, and that's as a square root. So we are reducing the number of protons we're imaging in each voxel, but we're also reducing the noise, right, by radical 2 because we're introducing extra measurements. So the SNR is going to let's look at the actual numbers. It's a little easier to see. So here, SNR1 is, of course, the signal to noise ratio. When you double the matrix size and the phase direction, we have the signal because of there being half as many protons. But we're also reducing the noise because of the increased number of phase encoding steps adding information. Right? So it's going to be over radical 2. Now when you replace and solve this, you end up with the signal is divided by 2, the noise is divided by square root of 2. In order to get rid of this, you multiply both the numerator and the denominator by square root of 2. They cancel here, and you end up with square root of 2 over 2 times the signal to noise ratio, which simplifies to signal to noise ratio divided by radical 2. Did I lose anyone? Good? Everyone's good? Good. Glad to see that. All right, so again, image doesn't look good. You want to double the signal to noise ratio. How are we going to do it with these 4 choices relative to that one? So in this one, there's differences in the matrix sizes. Notice that the first number is the phase matrix size, and the second one is the frequency matrix size. Oh, that doesn't look good. Most of you said D, which is correct. Very good. Okay, so why is it not B and why is it D? Well, since since it's under the square root sign, in order to double the signal to noise ratio, we would have to divide the matrix size and the phase direction by 4. Now, none of the choices allow you to do that here. 196 is not a quarter of 512. It would have to be like 128 or whatever half that is, 98. So less. So that is not the correct answer. Here instead, 256 decreases it by radical 2, and then you look and see is there another factor that's also increasing by radical 2, and there is. We've increased the nex from 1 to 2, which will also increase it by radical 2. So you can change multiple parameters to boost your signal, right? Having the number of matrix phase steps will increase the SNR by radical 2, and doubling the nex increases the SNR by radical 2. Radical 2 times radical 2 is 2. So the SNR is overall doubled as a composite of those two changes. Questions? All right. Moving right along to receiver bandwidth. This one's pretty abstract, but let's talk about it. There's a good way to think about it that will at least get you to the right answer on the test. So the receiver bandwidth, remember, that has to do with the range of frequencies we're listening to when we collect the echo. And it's directly proportional to the frequency encoded gradient, right, and how long it's on for. So an increase in the receiver bandwidth is going to decrease the SNR, but as the square root. Why does it decrease? This is, I found, the best way to think about it. There's some more convoluted ways to think about it, but basically an increase in the receiver bandwidth is an increase in the range of frequencies received or listened to. An increase in the range of frequencies received or listened to actually increases the noise measurements, right? So you're not actually doing anything for your signal, you're just increasing the noise. An increase in the noise, of course, will decrease the SNR, but because of the randomness of noise, as we've seen in multiple prior examples, this decrement is going to be as the square root. Think of the bandwidth, receiver bandwidth, as a frequency filter. White noise is basically what we're hearing when we're looking at the MRI signal. And white noise, by definition, means that it's constant across all frequency, right? Otherwise, depending on what frequency it's at, you can give it other names like brown noise or whatever. It doesn't actually directly correlate to colors, but before I digress, we're going to think about it like this. If you only listen over a 4 kilohertz range, let's say, in your receiver bandwidth, you're going to get less noise than if you were listening over an 8 kilohertz range. So let's just say this is white noise, right? This is what potentially exists in your oscillating protons in the magnetic field, right? And it's relatively constant across all the different frequencies. So if you're thinking about the bandwidth as a frequency filter, when you have a really wide bandwidth, you're listening to all this white noise superimposed upon the signal that you're listening to. If instead you're using a narrow bandwidth, right, then you're listening to much less noise superimposed upon your signal, to the point where it's going to significantly decrease the amount of noise in your data collection, which is going to improve your signal-to-noise ratio. Yes?
Why would you ever want like a larger bandwidth then? Why wouldn't you just want to make that like closest to 0 as possible?
So why not just use a lower bandwidth? Excellent question, Omi. Yeah, exactly. We discussed this beforehand. Well, because a low receiver bandwidth is going to result in a longer minimum TE, which might not be good if you're doing fast imaging. More chemical shift, longer echoes, you get spatial distortion. Forget about it for now, is my answer, because there's more, know that, it's cute there. Know that the spatial distortion, all of these issues are going to come into play more when we talk about other stuff later. Basically, you would just be memorizing it now. So know that there are reasons to have more or less bandwidth, and just remember it as the frequency filter thing. And if the bandwidth happens to be large, you'll have more noise and decrease the SNR as the square root. Okay. So this is the part in the lecture where I decide to diverge on a Red Bull-inspired tangent about why textbooks are wrong, or I just teach you what you need to know for the test. Because there's two ways to describe how the matrix size and frequency direction affects your SNR. There's the textbook way, which is that it's an indirect relationship as the matrix size and frequency direction, which is likely to be the correct answer on your test. But there's the way that I think of it, which is that it should actually be the square root. And I think I have proof for this, but it's not something that is going to really help you in the real world. So I'm going to focus on the textbook way, and then maybe if people want to talk about it later, I can tell you why I think it's the other way. But so yes, for now, let's just think of it as matrix size and the frequency direction. This often presents a challenge to people because it's different than the matrix size and the phase direction, so people have a hard time remembering it. It's like, oh, which one's under the square root? So we're just going to try to think about it this way. All right, it's almost identical to the matrix size in the phase direction, except it's actually easier because you don't have competing things. So MSF is the matrix size and frequency direction. What does that equate to in reality? When you break up the echo that you record, right, we have analog to digital conversion, the number of data points that you convert that echo into is your matrix size and the frequency direction. That's where that goes in terms of your real-life imaging. Okay, now, an increase in the matrix size and the frequency direction causes a linear decrease in SNR as an effect of its effect on signal. Much like when we increased it in the phase direction, we're dividing up our pixels into smaller areas. So if we double the number of frequency steps, then we have the width of our pixels in the x direction, and thus we're imaging half as many protons. And if you're imaging half as many protons, then you're decreasing the signal by half. Okay. Now, whereas with the matrix size in the phase direction, you were decreasing the signal by half, but you partially made up for it by increasing the number of measurements you took, which is why it then turned out to be a net under the square root. We're not increasing the number of measurements we do, right? We're just increasing the number of digital points in our conversion of our echo. So it just, like I said before, with MSP, cut it in half, but it added signal back by increasing the number of measurements. Here, it just cuts the signal in half because of your loss of number of protons. So that's basically it. If you double MSF, you divide your signal by 2, and the resulting signal-to-noise ratio is 1/2 the original signal-to-noise ratio. That's it. Pretty easy. And then Billy Mays is going to try to convince you to listen to me on my soapbox, but I think we'll probably skip over this for the purposes of so a little bit of a review, and then I go into how it actually relates back to sampling time, which is something that people don't usually consider in the textbooks. And as a result of sampling time, the MSF actually does increase the amount of time you spend listening to an echo, which would partially undo it. But I'm not going to go through that because it'll just confuse you. So, okay, so basically, yes. So bottom line, textbooks favor this answer, that the signal-to-noise ratio is indirectly related to the matrix size and the frequency direction, just as a function of dividing up the pixel further and decreasing your signal-to-noise ratio. So let's do an overall broad bird's-eye view review of this equation, which I want you to know and be familiar with. This will literally arm you to answer any question they could possibly ask about changing signal. K is the constant that represents, that's just the trash bin where we throw the fact that it's a spin echo and it's a sagittal and it's this and it's that, whatever. And we just ignore it because it's not going to change from one image to the next. Field of view is the dimensions in real space. Field of view in the phase direction, field of view in the frequency direction, and slice thickness. Or if it's a 3D acquisition, right, same thing, then it's just the field of view in the 3 dimensions, is going to say how much real space you're imaging. Obviously, if you're imaging twice as much real space, you're going to have twice as many protons, and thus twice as much signal. Okay. The next, remember, that's directly correlated as the square root. And that's because signal increases linearly, noise increases non-linearly. Right? So the overall result is the square root of the factor that X is being altered by. Matrix size in the frequency direction is relatively simple. You're increasing the number of your pixels, which divides them up into smaller numbers of protons, so there's a direct linear relationship. Doubling the matrix size in the frequency direction will have your SNR. The matrix size in the phase direction and the receiver bandwidth are the indirect things that indirectly alter your SNR as the square root. Matrix size because you're decreasing the number of protons, but simultaneously you're giving a little bump to the signal by increasing the number of measurements you're taking, right? And that's why it's a square root and not like the MSF. And the receiver bandwidth, I want you to think as a frequency filter. Wider receiver bandwidth includes more frequencies at which to record more noise. So it'll decrease your signal-to-noise ratio, but as a square root, since noise is random. And that's it. Any questions? That's the overview. We'll go through a couple practice questions. Okay, so same thing. I'm going to double my SNR, starting with the parameters at the top. How do I change my parameters to double the SNR? Yes, most of you said the correct answer, which is A. Okay, let's look at why it's A. Basically, we're going for the frequency. Remember, the frequency, when we're answering test questions, is not under a square root. So if you have the matrix size and frequency direction, you double the SNR, which is the correct answer. Some people chose D where the matrix size is unchanged, but the bandwidth is cut in half. Now remember, if you decrease the receiver bandwidth by half, the SNR is going to change by a difference of radical 2, not 2. So it would have increased by 1.4. All right. If I quadruple the number of pixels in my image in the frequency direction, what happens to my SNR? Is it double? Does it quadruple? Does it get cut in half? Is it a quarter of the original SNR, or nothing? Doesn't affect it. You guys said. Okay. Most of you said the correct answer, which is that it's 1/4. So let's take a look at our equation so you can see it again. Now, we quadruple the number of pixels in the frequency direction. That means that the matrix size in the frequency direction is times 4. I want you to remember this one for the test, so if you have a 4 in the denominator, SNR is going to be 1/4 what it was, right? If you believe me, then it gets cut in half, but again, we're not talking about that, even though I insist on continuing to jab it in there. All right. Yes, quarter the original signal. So it definitely affects it, and it does not increase it because it's an indirect relationship. Any questions? Okay. If I increase my receiver bandwidth, what happens to the SNR of the resulting image? Does it increase, decrease, nothing, stay the same, or machine explodes? Increase the bandwidth. Good. Decreases the signal to noise. That is exactly correct. In our equation, receiver bandwidth is not in the denominator as the square root, right? So you're increasing the number of frequencies you're listening at, which increases the amount of noise superimposed upon the signal you measure, without increasing the number of protons. Okay. Why does SNR decrease as the square root of matrix size in the phase direction instead of linearly, as it does in the frequency direction? Is it because physically smaller pixels contain less protons? Is it because NEX is intrinsically linked to the matrix size in the phase direction? Is it because the receiver bandwidth is intrinsically linked to the matrix size in the phase direction? Or is it because adding phase and code steps simultaneously increases the SNR? So, okay, so most of you said NEX is intrinsically linked to the matrix size in the phase direction. I'm glad you guys said that. That is incorrect. But I actually just realized why that can be confusing, which I didn't know before. It's actually, okay, it's because adding phase and code steps simultaneously increases SNR. So let's go over this slowly. The matrix size in the phase direction, when you double that, it will have the signal based on physically smaller pixels, right? But then it gives back a little bit to the SNR ratio by decreasing the noise, right? Because you're doing more measurements. Now, when I say doing more measurements, I mean to say that necessarily the number of phase encoding steps is set by your matrix size in the phase direction. Each phase encoding step is an independent measurement, right? NEX is also a way of doing extra measurements, but increasing your NEX will just increase the number of times you do each already existing phase encoding step and average it. Does that make sense? Is there anybody who answered this that doesn't understand? So, right, so matrix size and phase direction is not at all linked to NEX. It's linked to the number of phase encoding steps, which is discrete from NEX. Okay, so why do subtractions, this kind of harkens back to the beginning of the lecture, why do subtractions often help make subtle lesions, let's say faint arterial enhancing lesions, more visible? Is it because with contrast you have higher overall signal, because you have lower overall noise, because you have a higher contrast to noise ratio, or because you have a higher signal to noise ratio? Most of you said the correct answer, which is higher contrast to noise ratio. Okay, so let's look at this. higher signal-to-noise ratio. While it is true that after giving contrast, you actually do have a higher overall signal, this is not true. The noise is unchanged. And as a result of having higher overall signal, you do have higher signal-to-noise ratio over the entire image. But that doesn't mean that it's easier to see a subtly arterial enhancing lesion, right? Especially if, let's say, if you had a subtly, if you had an arterial enhancing lesion in the wall of the aorta, right? I'm just like making that up, that doesn't really make sense. But when you gave contrast, it would make both brighter. It would increase the signal to noise in both, but similarly with one another. And as a result, the contrast would not be changed. Thus, you wouldn't be able to see it better. When you see something in an image, a lesion or a tumor or whatever, it's because there's contrast from your target and its background that makes it stand out more. So giving contrast and suddenly seeing a subtly enhancing lesion is because you've elevated your contrast to noise ratio. That's a core concept in practice, in radiology practice. Questions about that? All right, so that was it. That was the great balancing act that is MRI Signal. We talked about the results and the things that are within your control, how it changes the signal-to-noise ratio. And then next time we're going to go over how changing some of those other parameters that I kind of skipped over, TE, TR, how that changes the actual image weighting or contrast weighting that you see in the images. Any questions? No, that's it. Thank you.